All right, so this is kind of a neat demo, which is the falling stick demo using a stick, a nail, and a lime. And what we're going to do is it really helps show that not all parts of the stick are moving at the same rate, right? Every part of the stick has the same angular acceleration, but every part of the stick has a different tangential acceleration. And so this kind of really shows conceptually how that's true. It's also really helpful for the sort of lost a lot problem, which is I think 610 number 7. The initial part of the problem, everything's static. Guy's on a drawbridge. The tensions of the strings holding the drawbridge up, and then the string breaks in the second problem, and you got to figure out the angular acceleration of the bridge and some other stuff. So we'll show the demo, and then we'll talk about how that applies. So we got meter stick, got a nail here at 80 centimeters. It's hard to see in the video. And we're going to take this line, and we're going to put it at 100 centimeters. We're going to lift the stick so that the line is directly above where the nail will end up, right? So that's what the ring stand is for, to give me a line of sight to line things up. And then we'll just give it a 3, 2, 1, boom. And look at that. We have impaled the line on the nail, right? So what does that mean? What that means is the nail got to the ground before the lime did, okay? So that means the lime was not in contact with the stick. It actually fell in a vertical line, accelerated at 9.8 meters per second, which means the nail, which traveled in an arc, was traveling or accelerating at a rate higher than 9.8 meters per second squared, because it was able to get to this position at a less time, allowing the nail to then fall on it, right? So what does that mean for the Sir Lost-a-Lot problem? What that means is when the string breaks, Sir Lost-a-Lot loses contact with the bridge and is no longer applying a torque. Right? Take a look here. All right, here's our demo. The only thing then acting is the weight of the stick. We don't have a torque from the lime here, even though the lime was initially resting on the stick. As soon as I released it and allowed the stick to start to accelerate, the lime went into free fall and no longer was in contact with the stick. We can see then the torque is just due to the weight of the stick and its perpendicular component. So it's an mg cosine theta acting at L over 2. It's a stick rotating at 1/3 ml squared times the angular acceleration. So we can solve for our angular acceleration, 3g cosine theta over L over 2. Which does mean the angular acceleration is a function of theta. The torque is not constant. All right. As that angle changes, we reach a maximum torque at horizontal, a minimum torque at vertical, and it increases according to the cosine function as it falls. What that also means that at any time or any angle, we could also find the tangential acceleration at different radii away from the pivot point. This part here, the pivot point is not accelerating at all, right? It doesn't move, it's just pivoting, but it doesn't actually change its position. And then along the stick, the different parts of the stick have to tangentially accelerate at different rates based on how far they are that pivot point, so that they can all have that same angular acceleration. So angular acceleration the same everywhere, but that tangential acceleration is growing as we go further from the pivot point, which means there's some point here where the tangential acceleration is greater than 9.8, and any point past that on the stick, objects will fall off the stick when released from rest. So that's your Sir Lost-a-Lot. He's chilling, and as soon as that string breaks and it falls, he's going to get left behind and fall off the bridge, not causing a torque. Hope that's helpful. Look at the video on that problem specifically, and we'll go over the math.